All right, guys, hello and welcome to another physics video lecture. Today, we're gonna be reviewing Newton's laws and forces. All right, so as we're going over this, be sure to copy down the notes and even more so, make sure that you are copying down the practice problems and going over them, writing them down and putting the numbers in your own calculators. Because remember, I like to say, don't learn to cook by sitting in the kitchen, right? You gotta get your hands dirty, okay? You gotta actually go through these and make sure you can solve them, okay? All right, let's get started. So the first thing we're gonna talk about are Newton's 3 laws, all right? These are things that everybody's heard, and the first one I'm sure you've heard a million times, all right? It says that an object in motion stays in motion, and an object at rest stays at rest, okay? We like to add the other part that most people don't say, which is unless acted on by an unbalanced force, okay? This is called the law of inertia. Inertia is the tendency of an object to not change its motion, meaning if it's at rest, it wants to stay at rest, and if it's in motion, it wants to stay in motion at the same speed, okay? The only thing that affects an object's inertia is its mass, all right? This makes sense. The bigger an object, the harder it is to get it to start moving, and the harder it is to get it to stop moving, or to speed up, or to slow down, all right? So this is Newton's first law right here. Now this idea of an unbalanced force, okay, we're gonna see next in Newton's second law. Newton's second law is an equation. It tells us that force equals mass times acceleration, all right? So it's a pretty simple equation, all right? So what we see here is that in order for us to have a force, okay, there has to be acceleration, okay? Everything that we talk about in this class has mass, right? So there's always going to be a number that's mass. Mass is never zero, so that our acceleration can be zero. And we have words for this, right? If the forces are balanced, that means that the total force is equal to zero. And if the force is equal to zero, that's because acceleration is equal to zero. Meaning if the forces are balanced, they're not accelerating, which can mean one of two things. Either the object is at rest, and it wants to stay at rest, or the object is in motion, and it wants to stay in motion, meaning it wants to go in the same direction with the same speed, okay? So remember, acceleration is either a change in speed or direction, and this is gonna be important later, okay? But if the object is speeding up, slowing down, or changing directions, okay, it's what is called an unbalanced force. And unbalanced forces have a net force that is not zero, which means that they are accelerating, meaning they are either speeding up, slowing down, or they are turning and changing directions, right? So let's do a practice problem with this. Okay, so here we got a little kid pushing a car. We have 4 forces at play here. We have gravity pulling the little car down, okay? We have the normal force, which is the ground, making sure that the car does not sink into the ground. We have the little kid giving an applied force, pushing the car forward. And we have friction pushing against the car, slowing it down. Whenever you see one of these free body diagrams, the first thing you have to do is you have to find the net force, or the total force. So how do we do that? Well, you look at the forces going in opposite directions, and you subtract them. If you have forces pushing in the same direction, you add them, because they're helping each other. None of our forces are going in the same direction, so we're just going to subtract them. Now, look at the gravity and the normal force. We have 80 newtons going down and 80 newtons going up. That means that these forces are balanced. They're equal. 80 minus 80 is 0. And that means that the car is not accelerating going up or down, and it's not, it's staying flat. But here, friction and the applied force are not balanced, so we have to subtract them. And that gives us 45 minus 5, which gives us a net force, okay, equal to, we'll draw it like this, 40 newtons. So our net force actually looks like this. It's 40 newtons, and it's going to the right. Why? Well, because the applied force is bigger. Now, this is asking us to calculate the acceleration. So we want to find the acceleration of the object. Well, to do that, force equals mass times acceleration. We know our force. Our force is 40 newtons. And we know our mass. It tells us. You got to remember, kilograms always measures mass. So we write down our equation. Force equals mass times acceleration. And we just plug our numbers in. Force is 40. Mass is 8 times the acceleration, which is I don't know. So we're trying to figure out that acceleration. So we want acceleration by itself. That means we have to move the 8. This is multiplication. So we do the opposite of multiplying, which is dividing. We divide both sides by 8. 8 divided by 8 is 0. And 40 divided by 8 gives us an acceleration, if I can use the right side of this, equal to 5 meters per second squared. And this is a great example of a complete second law problem. You start with a diagram, you work all the way to figuring out the acceleration. And the equation's not hard. If they give you the force and the mass, you can find the acceleration. Obviously, if they give you the mass and the acceleration, you just multiply them to find the force. And if they give you the mass and the force, you can find the acceleration like we just did. All right, so this is Newton's second law. Now, next, I want to talk about the other aspect here, okay? Here, we said that an object experiences a force if it speeds up. You're okay, thank you. If it speeds up or if it slows down. But it also experiences a force if it's accelerating because it's changing directions. We call this centripetal force, okay? This is the force of an object changing directions, turning, moving in a circle, all right? Now, it's important to notice here two things. One, look at this pink line, okay? That is the velocity. The velocity is always tangential. Okay? I didn't write it down because I didn't have a lot of space. But this is the tangential velocity, okay? And it's always a tangent to the circle, meaning it's always 90 degrees to the radius, which is half of the distance of the circle, or from the center of the circle to the outside. Okay? In order to find the tangential velocity, we take the distance around the circle, which is its circumference, 2 pi r, right? You remember that from like 6th grade math, right? Divided by the time it takes to go around. So it's still the same equation. It's the distance around divided by the time around. Distance divided by time is velocity. To find the acceleration, okay, this is called centripetal acceleration. And it's centripetal because it's always pointed towards the center. I know it might be hard to look at, but that blue line is always pointing right to the center of that circle. So this is something that's really important. You'll see this on a lot of questions. The tangent, or the velocity, is always at the tangent. Okay, it's always at 90 degrees to the radius. And the acceleration is always pointing towards the center. To find it, we go velocity squared divided by the radius. Easy enough. Last, you might ask you to find the force. In this case, it's the centripetal force. Okay, much like the acceleration, it's centripetal, which means it always points towards the center of the circle, no matter where it is. And to find it, it's literally just the mass times the acceleration. Okay, let's try a problem. Okay, so here we have a 2,000 kilogram carousel. So let's write down what we know. All right, so our mass here is 2,000 kilograms. The carousel has a radius of 8 meters. So we know our radius here is 8 meters. And it completes a rotation every 40 seconds. So the time around is 40 seconds. How much force does it have? What is the centripetal force? Now, this is a big dog problem, and it shows us every aspect of centripetal force because we got to find all three things. The first thing we got to find is the velocity. So let's start there. So our tangential velocity is equal to 2 pi r divided by time. Okay. So we plug in everything we know. Our velocity is equal to 2 times pi times the radius, which is 8, divided by the time around, which is 40. Okay? And to find this, we're going to need a calculator. So I should have my calculator queued up right here. This is going to be a little sloppy, kind of messes it up, but you can see right here. So we're going to go 2 times, I don't know if you can see it, but here's pi right here. There it is. Times 8. And that gives me 50.2. I'm going to hit enter. I'm going to hit answer. And we're going to divide that by the time it takes to go around, which is 40. And this gives me my answer, which is 1.256. So we'll round that up to 1.26. All right, so now I can take this, and I'm going to add this over here. So now we know our velocity equal to 1.26 meters per second. Step 1. Step 2 is to find the acceleration. Acceleration is equal to the velocity squared divided by the radius. Okay, so we know our velocity squared. That is 1.26 squared divided by our radius, which is 8. Okay, we go back to our calculator. We clear? Okay, and clear. And we're going to go 1.26. We have to square that, so hit the squared button, hit enter. That gives us 1.856776. And we're going to go answer divided by our radius, which is 8. And this gives us 0.198, which we're going to call 0.12. Or 0.2, excuse me. So now we have our acceleration, which I'm going to put here. Actually, does this look terrible? Can you see this? It's 0.2 meters per second squared. You see how the list just keeps growing? This is why you keep a list. Okay, good. Now that we have the acceleration, the last bit is the easiest. To find the force, we just take the mass and multiply it by the acceleration. Our mass is 2,000, and our acceleration is 0.2. We don't have to move anything, we just have to put these numbers in our calculator. I clear all this out, and I do 2,000 kilograms times 0.2 meters per second squared, and that gives me my answer, which my force is 400 newtons. Beautiful. That is a full problem. This is a big dog problem. Keep it up for a second. All right, we're getting there. The next thing that we need to talk about is sometimes the force is not at a perfect perpendicular 90-degree angle, right? Remember in this problem, right, we saw that it was so easy to add and subtract these because they were going perfectly up and down and perfectly left and right. Well, sometimes we don't get that, okay? Sometimes we have angles in our forces. And what we need to do is we need to break those angles into a horizontal and a vertical component, okay? When we do that, it allows us to add and subtract them very easily. And the way we do this is by using sines and cosines. Now you can go back to my lecture, I'll explain SOHCAHTOA and how we derive these equations, but we're just gonna use the two equations for right now, okay? We have our horizontal component, which is what we call Fx, right? And to find that, all you do is you take the total force and multiply it by the cosine of the angle to the ground. Now we have the vertical component, Fy, the one that's going up and down. To find that, you take the total force, right, and you multiply it by the sine of the angle. Again, the way that I remember this is that x comes before y in the alphabet, c comes before s. Little mnemonics like that are lifesavers when it comes to answering these problems, okay? It's an easy way to remember this. All right, so let's look at an example. All right, so here we have an angle with the horizon of 60 degrees. We have a total force at that angle of 1,000 newtons. And we want to know what's the horizontal component of this force, okay? Well, to find this, actually I'll just do it over here so I can bring the calculator over there. The horizontal component is Fx, which is equal to F times the cosine of the angle, all right? So to find this, Fx, we're going to take the total force, which is F, which is 1,000, times the cosine of 60. That's it. You take the total force, and if you want the horizontal, use the cosine. So let's find this out. Go down, here, clear all. You can actually see it this time. So I'm taking my total force, which is 1,000. 0. 1, 2, 3. I'm going to multiply that by the cosine of 60. And that gives me exactly 500. You see how easy that is? All you got to do is enter it in the calculator. So my Fx is equal to 500 newtons. Okay? That means we have 500 newtons going this way. And you know, just to do it, let's find the y component, the Fy. To do that, instead of using the cosine, we just use the sine. So I'm just going to clear this out, and I'm going to write it down. We do the same force, 1,000, and we're going to multiply that by the sine of the angle, which is 60, which gives us 866. And voila. Now I know that I have 500 newtons going to the left, 866 newtons going up. It makes sense. This angle is more than 45 degrees, so I'm going to have more force going up than I am going over. And now you can easily add and subtract this to the gravity or the applied force, and it makes it much easier. Okay. Next, I want to talk about Newton's third law. This is probably the easiest of all the laws, and it's the one that people make simple mistakes on the most. Okay, here's why. Okay, here's Newton's third law. And I'm sure you've heard this. For every action, there's an equal and opposite reaction. Okay. Now the thing that people need to understand, okay, is that it doesn't matter if an object breaks or bends. The amount of force, okay, the size of the force is always equal, and the direction is always opposite. So you'll see things where, you know, maybe if I punch a board and I break the board, people would think that the board experiences more force than my fist, right? My fist didn't break, the board did. But it doesn't matter if it breaks. That force is equal in size and opposite in direction. My fist pushes the board this way, the board pushes my fist this way with the same amount of force, okay? Just because it breaks doesn't matter, all right? That's just, that has to do with the size, the material, and how that affects the acceleration of that object, okay? So when you're looking at this, think about how you ride a skateboard or how you walk. When you walk, your ground pushes the foot, your foot pushes the ground down, and the ground pushes your foot up. Or when you skateboard, here, the kid pushes the ground left, right, with 50 newtons of force. So the ground pushes the kid right, with 50 newtons of force. It's how you move forward. You push down and back, the ground pushes you up and forward. It's also how books sit on tables, right? We've seen this before. This is the force of gravity pulling the book down, and the normal force of the table pushing the book up. Here the book pushes the table down with 20 newtons of force, and the table pushes the book up with 20 newtons of force. Always equal, always opposite. All right? Now the last thing we're going to talk about for today is universal gravitation. Okay? This is a big equation that all you need to know is how to put this into the calculator, and it makes it really easy. So all I have here is the equation, which is the force of gravity equals big G times the mass of one object times the mass of the other object divided by the distance between them squared. Okay? The thing you have to know is this big G right here. Big G, okay, is the universal gravitation constant. Oh, I should have put this. No! This is big G. There you go. I made a mistake. It happens. Big G is the universal gravitational constant, and it's equal to 6.67 times 10 to the negative 11th. It has units. We don't care about the units, okay? The units are, how does this cancel out? Meters squared, newtons, meters squared divided by kilograms squared. What's that mean? Yeah. Newtons, meters squared divided by kilograms squared. Anyways, it doesn't matter. You just gotta know this number. You don't even have to remember it. This number is in your equation sheet, okay? So let's see how to use it. Now something you need to remember is that you always measure from the distance of the center of the objects, all right? So if they give you a diagram and it shows you the distance to the center, you always have to measure that. If they just give you a distance, you just use the distance. So here we got a lot of information. So let's write it down, let's break it down, let's write down our equation. Here we're talking about Jupiter and the Sun and trying to find the gravity between them. So we know the mass of Jupiter, we're going to call that M1. Mass 1 is equal to 1.9 times 10 to the 27th kilograms. It's the mass of Jupiter. The mass of the Sun is M2, and it's equal to 1.99 times 10 to the 30th kilograms. This might not seem like it's that much bigger, but it is 1,000 times bigger. Okay, the Sun is 1,000 times bigger than Jupiter, which is crazy. And we have our distance here. They are 4.8 times 10 to the 8th meters apart. And again, I'll write down big G. Big G is 6.67 times 10 to the negative 11. All right, so I'm going to write it down here so you can see it up here. But our equation looks like this. All right, force of gravity is equal to big G, 6.67, 10, negative 11, okay, times M1, which is 1.9 times 10 to the 27th, times M2, 1.99 times 10 to the 30th. Okay, so I just have big G times M1 times M2. You always do this the same way. And you divide this whole thing by the distance, 4.8 times 10 to the 8th. And you gotta remember that even though this is already a huge number, you gotta square it. So the only thing left to do here is to plug these numbers into our calculator. You can kind of see this. All right, so here we go. Let me clear all this. Okay, so we have to use the parentheses. That's why I moved this up. So we're going to go parentheses. 6.67 times 10. A to the b is how you get that exponent. Okay, negative 11. You got to go forward. You see how the cursor's still up there? We don't want that. So we're going to go forward to bring it down, close parentheses. Okay, we'll put in our first mass, which is the mass of Jupiter. 1.9 times 10. A to the b. 27, push forward, close parentheses, times the mass of the Sun, 1.99 times 10, A to the b, 30, forward, close parentheses. Okay, it's a very long equation. Does it take some time? Let me erase that last one. Does it take some time? Yes. But as long as you're patient and you plug it in, it's easy. Now, I'm going to hit enter. I have my answer right there. So I want to take that whole answer and we're going to divide that whole thing by the distance squared. So that's 4.8 times 10, A to the b, 8, forward, close parentheses. And remember, you gotta square the distance. You hear me say that a bunch. I'm going to back that up just by hitting that, and I'm going to square it. And then there's your answer. 1.09 times 10 to the 30th, or 1.1 times 10 to the 30th. That's your answer. All right, guys, so this has been your review on forces, okay? Use this, make sure that you work, make sure you, especially with questions like this, make sure you take the time to put this into your own calculator, make sure you got the same answer I did. If you didn't, find me at tutoring or send me an email, okay? All right, guys. Have a great day. Good luck on your test. I'll see you soon.